All right, we'll get started. So, hey, first of all, thank you. If you don't know, my name's Alex Weibel. I'm the president of BuildingLogiX, who will be presenting today, and joining me also on camera is Dan Fink, who has been my right-hand man for the better part of 10 years. So a lot of you know who Dan is, and he works with a number of you that are on the calls. But if you don't know him, he'll do a quick introduction. As I've said in the past, we started doing these lunch and learns probably 5 or 6 years ago. This is a Monday morning or Monday noon tradition for us, where we take topics, whether they're technical, whether they're leadership based, whether it's an opportunity for a co-op or intern to present a project that they're working on, and it's really become something that we've at least I look forward to. And we decided to try and open this up to a larger audience, and we've invited you and others here for the last few weeks, which we'll continue to do for the next several months, to try and share some of the things that we're trying to learn ourselves, and share with others, both internally and now externally as well. So appreciate you taking the time. We'll try and keep this as close to an hour as we can, because Dan and I do have lunch waiting for us, but we won't eat in front of you. Hopefully you've got something to snack on, or at least keep yourself occupied. And I'm excited to listen and hear what Dan's got to share with everybody here today. So I'll leave that to you then, Dan.
Thanks, Alex. Again, thank you, everybody. This is a topic that I always enjoy discussing, and I've been doing machine learning and we'll call AI related things, since grad school 15 years ago or whatnot. It's all been pretty much in the real world. So I want to try and keep this pretty pragmatic and realistic. But I felt like it was an appropriate time, and we've gotten a lot of feedback and questions just, in the last 12, 18 months around, AI, machine learning, technology changes, et cetera, and what that means for the industry, what that means for, our products and services, et cetera. So I feel like this is a pretty timely discussion, here in the heat of the summer. So this is going to be, heavy on AI and chilled water focus. I've been, looking back at some of the presentations I've done at our various connected campus summits, webinars that we've put on, either publicly or privately. And we've also had, various kind of meetups and local chapter groups in our office. And pretty much every time I, give a talk about AI, there's something new, and the PowerPoint kind of needs rebuilt and changed. So AI is nothing new. It's been around for a while, but how it's being used, the way people have access to it has definitely changed a lot. And I'm sure you all have had some exposure and experience to that. So thanks for taking the time. We are celebrating 20 years this year at BuildingLogiX. Where a lot has continued to change and evolve, and we try and keep up with that innovation. We're a small organization, but we have a lot of experience, and happy to share some of that here today. So if I can get my slide to click on. So really, I'd say BuildingLogiX is kind of research or delve into machine learning. Probably started back in 2019. I don't know if we have our friends from Vanderbilt on here at all. They were really the ones that kind of pushed us and kicked a couple ideas off that have led up to kind of where we are now. And really that was around trying to find creative, cost-effective ways to better optimize plants. How do we engage, some of this jargon in academia that sounds really cool and really smart, but doesn't always make it into our, controllers that get mounted in our new plants? Or, how does the gap get bridged between all this technology and, all AI that tech companies put out and what physically, is putting out chilled water? So this journey, we've been on it for a little while, and you can see some of the big BuildingLogiX milestones here, but we're really trying to get into what is our next gen of products. How do we continue to innovate, push the industry forward, and work with our partners? And so that's a big goal, of these webinars this year. So we are doing kind of one public, one a month. So this is July, as you can see what's ahead. Invites will continue to go out on the email lists. If we get other ideas and people want us to continue this, I could see us, on into 2026, or even kind of intermixing a couple smaller ones. We've talked about, maybe some targeted peer groups. So it's not just us presenting, but giving you all the chance to kind of talk and facilitate conversation on a topic. So please keep that in mind. Don't hesitate to reach out to us if you're interested. So, all right. When we get into AI, its role in efficiency, in particular with chilled water, I'm going to start kind of high level, and then you'll see we'll quickly get into some weeds and some technical stuff. So um, the perspective that I'm going to kind of talk through, and I'll say the type of equipment systems audience that I'm going to use in my examples as I go through is really the perspective of somebody that has a medium to large or district chilled water plant. So predominantly centrifugal chillers, 800-ton, 1,000-ton plants and bigger. So that's kind of, some of the examples and numbers that I'll throw out are going to kind of be with that context in mind. And then my goal for today and what I hope you walk away from is really three things: kind of awareness, education, and action. So a little bit on, if you're interested, if you want to pursue this or are pursuing it, what are some takeaways you can have? How if somebody asks you about this, internally, or you're trying to deliver something for a client externally, just a little bit of education on some of the under the hood. And again, this is kind of geared towards a more technical audience. This is part two of our, chill water series. So we are going to get a little nerdy here in a bit. Alex, I see you smiling. Is there something you have to add? Okay. All right. So when we think of chiller plant efficiency, a lot of times it comes back to the chiller, right? That makes up the biggest load in the plant. That's the biggest driver of plant efficiency. A lot of times with chiller selection, you're trying to meet ASHRAE 90.1 guidelines. It's two numbers depending on, what bucket you fall in. A full load efficiency and a part load efficiency, which, is an average of different load conditions over the course of the year. So that's some of different targets and what chiller manufacturers try and meet. And then if you have a newish chiller, the factory probably gave you some performance specs that might look like what we have on here. They're all required to go through the RE performance testing. So if you don't get performance data from your chiller manufacturer or the engineer or the contractor putting it in, I would definitely encourage you to do that. That's a very fundamental point to kind of sanity check where you fall. It's an easy starting point to kind of gauge things, hold people accountable. But this is what one typically might look like. So this is a machine that it's a 2,000-ton chiller, 200 GPM flow. It gets, its best efficiency at about 30% load. You can see at low loads, there's a runaway effect, and then there's kind of a linear increase as time goes on. So this is just one chiller of one design. So all different kinds of chillers are going to have different profiles. So if you have a plant that has mixed chillers or chillers of the same type but different vintages, your efficiency curve and sweet spot is going to be different across all of those machines. So that's one kind of thing to keep in mind as we go through to understand, what role does AI have in this. The other thing is chiller efficiency is heavily driven by a lot of stuff that's outside of the control of the chiller. So there can be a lot of smarts and a lot of data in new chillers. But if that isolation valve or butterfly valve that's not on the BAS is, somebody override it or tweaked it a little bit during maintenance or trying to check something out, didn't get it put back. It's one of many things that can impact plant efficiency. So there's kind of this game you're playing with AI and, data analysis as far as like what are impacts, changes, optimizations we can pinpoint to, and then where are our blind spots? Because about half the time, and this is kind of speaking from experience, you'll be able to detect an issue and a change in a time period and even quantify the savings impact on a performance degradation, but not all the data is available to view. Some of it might never be available to view. And so you're kind of making inferences on what the root cause fix. And oftentimes, it's this pairing of, the service tech or working with somebody on site to really, marry those visuals and physical diagnostics with the digital. So, that first chiller efficiency chart I showed looked like this really nice curve. Oh, we should be able to pinpoint, our chillers running exactly like this. But in reality, there's a bajillion other things that come into play, even on identical machines in identical plants. You could have a sensor calibration on a brand new chiller. You could have a slightly different refrigerant charge. You could have VFDs or electronic equipment not working right. Maybe the piping into the machines is different. I mean, it goes on and on. All of these things result in kind of just this scatter and data blob of what your plant efficiency might look like. So part of what AI can do beyond optimization and fault detection is also trying to help bin, cluster, categorize, do pattern matching to better understand as a starting point, where your plant's currently operating, what's your baseline. So this is an example of a real plant, 365 days of 5-minute data plotted on here. You can see, as tonnage goes down, plant efficiency gets worse, especially at higher wet bulb conditions. You can see at low wet bulb, low tons, the plant is in its most efficient, 0.4, 0.5 kW per ton. You can also see here the color changes based on water temperature from the cooling towers. So, this is a graphic that we've made in BDX for a client. But really, there's other things that come into here. How many chillers could be running? What's your evaporator temperature, right? So there's all kinds of variables that really, narrow down on, is this the best point in which I could be operating? That can be a lot to look at. So this is, kind of the Dan benchmarks. You can find your own stuff online, but there's a lot of things around chillers. There's less around plant benchmarks and where you fall in kW per ton. So to marry kind of the sniff test with, the detailed analytics, this is, kind of rough order magnitudes. Feel free to debate me on this, but kind of rule of thumb here, at a full load plant, peak conditions, the top 10% of the year, top 20%. If you're a reasonably good plant, you're in the 0.6, 0.7, even 0.8 kW per ton range. That's kind of a sanity check, a ballpark. In today's day and age, if you're above 0.8, I would say, that's pretty bad. You're in the worst of your peers. Really, between the 0.6, 0.75 range is kind of a, good full load benchmark. And then if you're lower than that, obviously, you're doing some things right. Under part load conditions, say the best plants can get down to like 0.4 kW per ton, right? This is full mechanical cooling. We're not talking about water side economizing. I've seen some under, perfect conditions. You're running in the winter time. You got a small steady state load. You could get a little lower. Some people are going to talk about heat recovery chillers and constant loads on data centers and, be able to argue some efficiency numbers. But really, this is, high level, some rule of thumbs, and then, kind of a water side economizing. Your chillers aren't running. You either have plate and frame or, parallel through a machine. Your cooling towers are driving cooling. You can kind of get down in this low range for a certain time of the year. So people always ask this question. I haven't at least found, feel free to chime in, but I haven't found a lot of documentation online evaluating or benchmarking full plant kW per tons, kind of how whole building energy benchmarks work with Energy Star and, a typical hospital versus a grocery store versus a K-12 schools. Those don't really exist for plants. A lot of the focus is on the chillers, and, to some extent that makes sense. But I wanted to share, just a little bit of our experience and our take. So what goes into the plant kW per ton? Where can you have the biggest impact? How does AI play a role? So if you're looking to make, the biggest efficiency improvement in your plant, this is kind of stating the obvious, but if you have an existing plant and you have old chillers, likely getting a new chiller is what's going to drive your kW per ton down the lowest. New chillers, in the last 5, 6, 7 years are a lot more efficient than machines that are 15, 20 years old, end of life. And so if you're kind of considering options, how do we prioritize plant upgrades? How do we plan obsolescence for the long term, that types of things. If you have a good engineer working with you and you are getting, new chillers of the predominant manufacturers, that is going to give a big boost to plant kW per ton. The thing to keep in mind is, are those machines more efficient at full load or part load? And that's really where your engineering partner and firm come into play. Those are some questions I would ask. The other kind of big blue one that requires a lot of investment, it takes a lot of time, that can have a positive impact on kW per ton, is really the load side. Again, out of control of the chiller, the plant controls, plant operators. Do you have two-way valves, energy valves? Do you have good building DP sequences? Do you have building pumps, right? All those things come into play, whether you're a centrally connected loop or just a big plant for a big building. again, that is, more capital intensive project based. The ROI on those blue ones can be kind of long. You might save $200,000 putting in a new 200-ton or 2,000-ton, dual compressor fancy chiller, but that could be like a $750,000, $1 million or more project. So it's important on how you be strategic. The two green items in the middle are really where data analytics, AI shine, the operational efficiency and controls optimization. So they don't necessarily drop plant efficiency as much as those two big end ones. However, operational faults like a divider plate gap, an expansion valve issue, a refrigerant charge issue, a sensor out of calibration, those things can cause changes in plant kW per ton that are measured in the tens of thousands of dollars each. Same thing on the control side. If you have bad staging, PID issues, you're not getting the optimal temperatures on either side, you're not staging at the right time, those can each have tens of thousands of dollars in savings. So a new chiller, yeah, you might be able to save and get $200,000 in efficiency savings in a big plant. But if you're pairing operational efficiency and controls efficiency together, it's also feasible that you can achieve, a six-figure savings number on a plant. A lot of it, again, comes back to the baseline and how far you're pushing it. So that's really where AI comes into play. So I see the role is on the optimization and the fault detection. And I kind of took this from something I really liked about Nexus Labs. If you haven't heard of them, they're a smart buildings group. They have a weekly newsletter, one of the more realistic kind of owner-driven groups, trying to push different avenues of, not just chiller plants, but smart buildings. And, a lot of people get excited about AI, but I think it's important to be realistic. And what I'm going to try and show as we walk through this conversation, it's a journey, it's a process. Some areas of AI you can bolt right onto your plants now and have a positive impact. Others, there's a lot of ifs, ands, and buts. And I feel like there's not always transparency in the market on what are those pieces and parts and things we need to know to make educated decision. So hopeful that's what you're going to walk away, because in the end AI breaks down significantly. If you have garbage in, you get garbage out. Sensors out of calibration. What if you don't have flow meters? What if you're computing power versus measuring power on your chillers? All those things come into play. And so in the end, I'm going to try and bubble this into some takeaways that are important to keep in mind, because really we're on this journey from building automation, HVAC, 20 years behind is kind of what people always say, to leading edge. We're trying to move from the cassette and CD area to the Spotify age. So, what does that take? And sometimes you'll have buildings and plants in the same portfolio that, are approaching Spotify level ease and sophistication, and others that are way behind. So, what applies to each in those scenarios? And oftentimes, a lot of them run into a bottleneck with building automation. So you can read this list for yourself, but there are folks, one of their biggest, I'll call it hindrances, can be the building automation system. And what capabilities do you have with it? How locked down is it? Who can program it? So that's something I'd encourage you to keep in mind when you think about optimization. So we're going to get into, kind of some more details, but I'm going to start with, kind of the real world example. And part of the reason people have asked us about this, AI is a buzzword, but there are a lot of different applications that are, becoming more prevalent in industries. So, how come building automation and our plants, run on these dumb sequences and waste a ton of energy? And, we always have problems, but there's all these other sectors out here that are able to, it seems like just in 3 years, they've completely transformed and are data driven and deploy AI and all this. Part of the reason is the number of players involved and the complexity of plants is a lot. Each plant is a snowflake. You have the owners, the design, construction, MEP firms, and you have the building automation, the chiller manufacturers. You might have in-house or external chiller service providers, and then commissioning agents all bundled in, hopefully trying to be integrated in some form onto getting a chiller plant going. But that same team probably might have never even worked together on, another plant, or maybe 2 of those or 3 of those groups have worked together before, but not on an identical plant. again, we're kind of ignoring the data center crowd for the time being when I talk about this. I mean, um, so how are the incentives tied to outcome, right? There's commissioning, you're trying to make sure the plant and the sequences are followed, but was there really commissioning on how good the sequences are in the beginning? Do you have the data to analyze or the performance specs on your chillers to make sure they're getting their right efficiency? What type of hoops are you going to have to run through downstream if you need to update a sequence or want to make a change? I feel like some of those are questions that, often get overlooked or ignored and kind of punted to the operations team years down the road. So part of my plea here, depending on what hat you wear on the call, and what I'm going to continue to kind of ask for is this isn't just a technology challenge or opportunity, getting advanced control AI into equipment and plants. It's really a process and industry mindset change. So, the DOE had the smart buildings or smart analytics campaign. There hasn't really been an equivalent of plants, or, this might be a little controversial, but I'm going to call ASHRAE Guideline 36 a little bit weak sauce on what they came out with to support advanced plant control. And I'll explain later kind of what I mean by that. So I think for the design, the MEP firms, there needs to be more visibility on data, sequences, technology options. I feel like some of these industry groups, instead of funding one PhD student doing a thesis that then goes away in a year or two, there's, owner partnerships, contractor partnerships that could take place to help drive this quicker along. The MEP firms, I view this as an opportunity. Show your smarts. Don't just do boilerplate, sequences on stuff. Explain to the owner all the work that went in, or why you might select a chiller, or why, what options do they have in that? What, upfront investments might make more sense. Take a life cycle approach, and that kind of goes for the owners too. Be clear on your outcomes. Be realistic with what can compare with your team and support staff and budgets. And also recognize downtime is still going to happen. You're going to have the best predictive software someday down the road. You got vibration sensors all over the place. Something is still going to happen to cause downtime. And, you can work to minimize that, for recognize that can happen, because it's not just technology, it's people and process too. And then for the chiller manufacturers, as somebody who's done a lot of research, into our own software about, different levels and starting point ranges to monitor, chiller health, there's not a lot of public information out there around, the big four chiller providers and, what are models or healthy ranges for stuff. They all have internal alarms, and some of the manufacturers, I'll especially call out the top two big ones there. They do a good job now with having a lot of data exposed in their backnet cards. The challenge is it's all up to the engineer, the software provider, or contractor to decide how they want to use it. I've had to go through and talk to centrifugal techs at different places to, hey, how would you approach this if you were using data? What metrics do you want to see? What limits? How does that vary based on chiller and vintage and refrigerant type? And it kind of feels like, the chiller manufacturers are trying to live in their own bubble and kind of keep their secret sauce to themselves a little bit. And I mean, they're a business, I get that. But I think there's an opportunity for them to, market and show, the performance of their equipment, get some more sales in if, a little more resources exist out there. So I'm going to get off my pedestal here, and we're going to get into the technical details. So we talk about AI, the buzzword, artificial intelligence. That is very broadly encompassing. It's basically anything that, runs on the computer that was some sort of, artificial algorithm sequence, et cetera, that humans, dumped on that brain power onto a machine. So a lot of what you hear around optimization, fault detection really falls within the machine learning bucket. There's other forms of AI, the language models and all that stuff, but, kind of what I'm going to focus on, what's most applicable, is in the machine learning. So in machine learning, there's different segments of machine learning. I don't have them all listed here, but this is kind of just an example. There's, unsupervised learning where, it's kind of like clusters, what you see on the thing. It's trying to find anomalies. There's supervised learning that's helpful in, predicting things. You're training it, you're giving it something, you want an outcome. There's reinforced learning where you're kind of weighting rewards, priorities, inputs, and outputs, constraining the AI to try and get better at something, right? So this is, yeah, maybe a little more detailed than a lot of people like, but I think it's important to be aware. So if you're entertaining software or ideas, you can start to ask questions, and this is a list of a handful of, players that will offer chill water optimization or chiller optimization. There's a lot more than this, honestly. They vary between big OEMs and one person, two-person companies, and then, medium-sized technology companies like ourselves. But the reality is there's not really transparency necessarily on what's happening across all of these. It's kind of like these Ben and Jerry flavors. I go, oh, these all sound good. I don't have time to sample them all. I don't know what, are there other things out there besides ice cream that, would satisfy my craving? So we're kind of in this still early adopter phase. And yeah, I think we're slowly here in the next year or two, hopefully trying to transition, to kind of push the envelope on what's possible, how both these products and others that will come out, serve the end user, the owner community better. On the flip side, there's this other perception, either AI is going to solve all my problems, why aren't we doing it? Or this is a bunch of, garbage, fluff, we're not going to entertain any of that. And I think, the truth lies somewhere in the middle. So I do think there definitely there's a role for AI and machine learning, and it can far surpass any other technologies to optimize certain things. And there's a spectrum, right? You can have machine learning just optimizing staging or cooling tower temperature, or you can have it controlling the complete plant. I know some people have talked about not just controlling plants, but also downstream secondary pumping DPs and air handler supplier temps and valve positions. I mean, you could go full Skynet if you have a big campus, but like a lot of things and new technologies, I think there's a migration path that,
Hey,
has
Dan,
reasonable ROIs. Yeah.
I dropped the ball a little bit. We did have a question going back a few slides around your essentially costs associated with new chillers, some of the optimization strategies, design strategies. Yeah, go back maybe one or two more. Can you give a level of maybe even projection? What does $3 signs mean compared to $1 or $2 signs?
Yeah, $3 signs is in the close to $1 million range, I would say.
Okay.
And again, this is kind of from the perspective of campus, so that or higher, right? It's the cost because you're adding capacity and putting in a new plant that costs $10 or $15 million, or you want to replace a large chiller that costs $500,000 to $1 million. Retrofitting 100 buildings with energy valves and changing piping, right? Those are big, seven figure type projects. Green is going to be measured in like tens of thousands to maybe 100,000.
Okay.
Yep.
All right.
And so the ROI difference, I mean, if you think of the blue, usually that's more than 3 to 5 years. I mean, you're pushing like a 10-year ROI. The
Right.
green is something that could be, less than a year, less than 2, maybe 3 at most, depending on what you got cooking. So,
Yep. Okay.
Yeah,
Thank you.
All right. So I think the BuildingLogiX take is really around data informed optimization. So regardless of whether you're using our stuff, you're using somebody else's stuff, it doesn't really matter. There's, I think, some key principles that we follow that really help say, is this worth the squeeze? Are we holding, either sequences or engineering firms, providers accountable? Does our team have the tools to address issues or faults that are detected to change stuff? So having a backbone of data, and when I mean data, it's not just, oh, I have a 7-day or 24-hour trend logs on a bunch of these points I can click through in the BAS. Do you have access to a year or more of 5-minute data on every data point you have? Can you get can you make a chart of anything you want in less than 5 or 10 minutes? The timestamps all clean. Can you trust the data? Do you have ways to find stale data? All these things come into play because ultimately data drives information and gives, you as the owner or the designer, the commissioning agent options. So to really move AI forward, data is a backbone of it. So when we look at specs or new plants that come online, I think we really got to change that narrative and make sure, we advance beyond just backnet trend logs that, are a pain to click through and whatnot. Couple pitfalls to be aware of. So people rightfully so have had bad experiences, with AI. So like any other control sequence, especially if you have, a really complex algorithm running that's trying to optimize and find the sweet spot on every variable in your plant, condenser flow, evaporator flow, chiller staging, all your temperatures, you can hit a couple pitfalls where you get yourself in a hunting state. And so, sometimes these algorithms are trying to push the limits to learn more, but go too far, and all your chillers shut down at once. Or you're always hunting around the most optimal set point, but you never get there because while your AI or machine learning sequence might be good, it wasn't tuned with your PID loops. And so your plant efficiency actually didn't change or might have even gotten worse. Right. So that is what I'm talking about with the having a data backbone paired with AI helps you hedge against some of this and make sure, during that onboarding process, things are good. Also, depending on what type of sequences you're deploying or what machine learning methods you're using, you might not have enough data to really optimize the plant. How do you know somebody's, not just trying to sell you something and, it might work great, but is it really pushing the limits beyond a regular reset? Another pitfall is some of these sequences and software packages and stuff, they're kind of a black box or they're super complex. How often do you have to maintain and update them? How do you know they're working? What's the ROI compared to other options? So those are some things to be aware of. And then in the end, overrides here, there, everywhere can completely negate what's going on. So it's important that if you're trying to do advanced chiller plant control, you get the buy-in of the people in the field, the operators. They have some input, some ownership, some understanding of it. That educational and training piece is really important because you might have the latest and greatest thing and it could be the sweetest control plant ever. As soon as somebody goes on and puts an override or two or doesn't trust something and changes a setting, all that investment could go to waste. So that's really a PSA to try and get, buy-in from boots on the ground. So let's say you got data, you got buy-in, you got some infrastructure in place. What's the secret sauce? How do we optimize our plant? What are the ways that you can do that? Is it worth it? So there's optimization and fault detection and machine learning algorithms. Some apply better to control versus monitoring. And I'm gonna kind of reference these logos, as I blast through some of these technical slides, but try and give you a quick overview. So top, or you might hear that in ASHRAE or through some engineering firms, that's really like the theoretical optimum. So I'm going to call this optimization that is kind of engineered, mathematically driven. It's not necessarily machine learning, but you can classify it as artificial intelligence. So think of, a well-implemented guidelines 30, ASHRAE 36 that the engineer actually modeled and was intentional about. There's also neural nets. So you might have heard like Google's DeepMind or, the way neurons and pattern and, all this complex association works. That's neural nets. Decision trees or decision ensembles. So, that's a big collection of, different coefficients and regressions and conditions that are paired together. That decision trees like XGBoost, random forests, those are ones I use a lot. I'm a proponent of those for somebody getting started. The Bayesian, the more like time series stuff. So that would be kind of the square logo here. These would be models and algorithms that focus on like sequential patterns, time series things. And then at the top, reinforced learning or transfer learning, those kind of fall into, things that are actively training themselves, trying to explore. They might be a little unpredictable or, kind of pushing the limits on stuff, trying to figure out, self-learning type of control versus all of these are more either engineered or forecast learned models. Then down from monitoring, some of the same ones apply, but I'll add in one other that's like K cluster or clustering where, it's appropriate for like anomaly detection, pattern matching. That's another one that comes into play. This list isn't fully extensive, but I did want to call them out because if you're entertaining stuff, I think it's important to be able to ask some of these details. Sometimes the fluff on AI comes from, well, somebody sold us this, $100,000 AI package and, oh, it sounds and is branded so fancy, but really behind the scenes and we reverse engineer it, all it is like a linear, x equals mx plus b type equation. I think it's important for engineering firms, consultants, owners to start to get more educated about some of this and, push people to ask the hard questions and, make products better. So what that might look like, let's say I'll use condenser water as an example as I go through here. You might have condenser water reset line that might look, like plus 10 wet bulb offset. But really, if you looked at a plant and you might use one of those models to try and find, that sweet spot under a variety of conditions, these might look like planes. And some of those, might just be changes in a straight line. They could be curved or nonlinear. There could be a ton of different variables that result in what is that most optimal point. So when it comes to, what algorithms shine in what territories, I mean, neural nets are known to be the most complex, kind of powerful models. They require, a lot of training, though, like how many different layers, how many inputs, how much are you feature engineering, how do you account for overfitting? Those are some of the gotchas with neural nets. And they're also CPU intensive. They can be a black box. So if you're like, oh, I'm going to give a neural net to my operator, he's going to know how to operate it. Even for engineers who deal with it, it can be so complicated. Like, it's what I would classify as a black box often. It's not something that you can just drop into Metasys or, even Niagara per se. They can be very CPU intensive too. So it's not always easy to run a neural net the edge or something like that, and you need a lot of data. As we go up the spectrum here, the random forest models, these require a lot less CPU. They're still data hungry. They might not work as well in very complex scenarios, but for plants, HVAC systems, they're thermodynamic. There's some predictability to them. They don't require as much horsepower to run. They can be ported to building automation systems. So I do see those as a more viable option for those who are looking to kind of experiment or try out things. Reinforced learning, I'd say, gets the most hype. It's something that, the claims that can be deployed easily. There's kind of this learning period, and then all of a sudden it'll get it, and just, your plant will be a rock star. I don't know if I would endorse it that far. We've done some reinforcement learning stuff. We continue to kind of evaluate it. There are trade-offs. The benefit is it can be deployed quickly. You don't need 6 months or 12 months data set on your plant. The downside is it can run your plant in non-efficient modes for a period of time, or if it's not trained right, potentially cause problems. I also think with reinforced learning, and one of the reasons people talked about transfer learning, where you teach AIs on simulated data before deploying them in the field, which is a lot more expensive and involved, harder for operators to, update on the fly. But one of the pitfalls there is like, well, there's so many different operating conditions of a plant. What if your model never actually sees it in the short term, like training window, and it's continuous evaluation? So is that really getting the best plant performance? There's some debate about that. Then the pattern matching, it's not necessarily good for control, but it is good for, pairing with control and fault detection. It does require a bit of engineering. Like you don't just slap it on there and be like, tell me what's wrong with my plant. You still have to have some, principles in mind and goals of what you're trying to find detections on and what you're going to use to train for those anomalies. And it is kind of a growing evolution of, what traditional rule-based faults is, but it can be intensive and very snowflaked. And, that's an area I think more data, more test cases from either ASHRAE, the DOE, or chiller manufacturers will continue to make that better. So if you were to question somebody on what their product entails, how it works, this is an opinion, subject to change in the years to come. But I think from a control perspective, the most robust is really a combination of those engineering principles. You had an engineering firm, they're using ASHRAE and thermodynamic principles, and they're pairing it with, advanced machine learning data analysis to give you a set of operating conditions. It's not something that's changing too fast or all the time. It's something you can validate against and retrain. The downside is if the plant changes, gets a new chiller, et cetera, you do need to, be able to modify and evolve with that. So that's where reinforcement learning shines. However, there's a lot of pitfalls, and I think a lot of variance in reinforcement and transfer learning that academia, likes to make a lot of claims around, but I haven't seen like fully implemented well in the real world. So I'd like to think this will get better in the coming 5 years, but I also don't think we're there yet.
Hey,
Monitoring,
Dan,
yeah.
maybe this is a clarifying question again from someone in the audience. So, are you saying neural nets, or do you have a starting with part data, or
No,
are you saying
you need a lot of data
okay,
for neural nets, and
okay,
I'll use them sometimes, but generally they're kind of the last in the bunch if it's something really complex and I have a lot of time to dedicate towards it, or it's a very like a neural net paired with another one of these algorithms, kind of like how Google DeepMind works, but most campuses, MEP firms, or tech companies like ourselves don't have 200 developers that I can dedicate to tweaking this one algorithm on this one plant. But the neural net paired with other models is really how you capture like nonlinear impacts down to the details. So someday if somebody comes out with an entire campus model, how do we control all air handler temperatures, pumps, chillers, towers, valves from one mind? A neural net would definitely be part of it. But
good.
yeah, in terms of like a targeted and starting approach, not necessarily where I recommend starting with.
Okay.
All right, so let's take this one step further. Condenser water temperature, that's a common one. We're not going to try and optimize the entire plant. Let's just start with one thing where there might be some savings on the order of, $10 to $50,000, let's say, or $70,000 if you're a big plant. Baseline period, if you have hopefully you're not running at a fixed 85-degree set point, but from there, if we follow these sequences down the paths of complexity, the boilerplate, see it in the spec +10 wet bulb reset. That's kind of the next best, but that is a big jump over a fixed set point. From there, you might have a variable reset. So you might be, at 50 degrees +8, at 70 degrees +10. Sorry, that's 70 degrees, 50 degrees wet bulb. It's hard to see, but think of it as a variable reset line. So the approach target changes with the wet bulb conditions. ASHRAE 36 kind of takes it one step further. They give a couple options. The first one, it depends on the variability of load in your plant, but really it looks at chiller lift and total plant capacity to then pick a reset point. And then their second option really just states pick a condenser water set point that minimizes plant power and increment 1 degree at a time. It's like, okay, thanks. How do you do that? What are the best options? Have you made sure what are all the sensors you need to achieve that? Because there are quite a few to do that accurately. And really, if you're optimizing a plant to this level beyond one of these resets, so I'll call this advanced row more, or the bottom row more advanced, you should be controlling your condenser water within 0.2 of a degree, half a degree, and you should have your towers and pumps and staging tuned to meet all that. Some people might say, oh, that's not possible, but in the real world, we do have cases where that is possible. It does require some effort, but is achievable. The next is what I talked about before, which really kind of pairing engineering, thermodynamic principles, understanding of the plant with a machine learning model with a data set where you kind of test and explore and then build a machine learning model that captures, all the humidity and load and time of day and all these other wet bulb conditions to produce, the best temperature set point. And then the last one's really reinforcement learning. So what type of savings, like what's the ROI, what's the value proposition here? So, I mean, going from a fixed set point to any type of reset, again, there's a lot of ifs, ands, and buts on your plant configuration. Is it variable flow? What type of chillers? What's the load, et cetera? But ballpark, I'd say 5 to 15% savings, total plant annual savings. So that's not insignificant. That can be a pretty big deal. That's again, what's your baseline? If you already have a plant that is doing, what you feel like a pretty good condenser water reset, you feel like the kW per ton target's pretty good. I don't know if you necessarily want to go invest tens of thousands or $100,000 more in like a software product if your operators are comfortable, if you're pushing, catching faults with your data, you're tweaking your resets, or maybe you have some seasonal conditions on there. So it's not overly advanced, but you still have smart logic. You can still get a lot of savings out of it. So going from, a variable reset to hash rate 36 or any of these other models, machine learning I talked about, if you're taking this incrementally, you're really talking about, 1, maybe 5% more at best that you're going to squeeze out of it. So again, there's considerations that you'll have to answer on, what's most appropriate for a plant. Any dads who are engineers who are doodad fans, his phrase, well, this will be 1,000, that'll be 1,000. If anybody comes back to you and you don't have a condenser water reset, even a basic one, and says, oh, that'll be about $10,000 to program. If all they're doing is programming, there's no data analysis, there's no visualization or reporting, there's no machine learning, that's a pretty steep price tag. Pretty much any modern BAS on the front end, you could pass supervisory control down, or even at the device level, depending on where you're putting your logic. This is something that, yes, you want to check and test it and validate it and make sure the overrides work and there's fallback logic. So this isn't just like a 15-minute dump or reset on to do it right, but it's also not egregiously expensive. So for a basic reset, that's expensive. Now, if you wanted to go to a more advanced mode on one of these, generally they do require more involvement because there's engineering time, you need data, there's modeling, you want some verification. I think if you're trying to push the limits, you need to be able to show and target, and your team should be actively whoever's the operator should be seeing kW per ton, whenever they're looking at the plant, along when they check, the loop temperatures and chiller status and stuff like that. You should be seeing kW per ton. So, this is for those who are trying to, push the limit, be the most efficient, showcase they're smart. So pretty much any BAS, I would say, can handle guideline 36 sequences. Like I said, they require a bit of calculation and data points available, but I know they can be implemented. I've seen them in quite a few. That shouldn't be a challenge if your controls providers, giving pushback, trying to understand that, or, you can always ask us for some 2 cents on that. When it comes to deploying machine learning models or the next phase of it, really the only BAS of that group that I've seen that can legitimately do that would be Niagara. Again, that's not out of the box. That requires somebody sophisticated in Niagara to know how to do that. And there's a couple different ways you can do that. Other building automation systems might claim that they have, sweet sauce or cloud integration or something like that might work. Personally, I haven't seen as much of those be successful or fully implemented. We do use Niagara 4 in cases like this, and I've seen other people do the same, and I know quite a few other optimization providers also use that platform. So in terms of going from hash rate guideline 36 to the next, I know a very few other than that one. When it comes to reinforcement learning models and all that, transfer learning and real-time learning, it really, in today's day and age, is one of those specialized backnet programs or integrations that is probably passing something to the cloud and going back and forth. And I'd say I'd vet those very thoroughly. And again, before you even get to that point, benchmark where are you at on kW per ton? What are the biggest things causing plant performance? Because if you're trying to put reinforcement learning on a plant that's got 15, 20-year-old chillers that have a few data points, or maybe they're not variable speed, you're putting the cart before the horse. So some fundamentals. Yeah.
Quick question. And Nick talked about kW per ton and kind of how we calculate and look at that. If you know the answer to that question, and you're somewhere in the 0.7, 0.8, which would be on the higher end of the spectrum, as you talked about earlier, where's the starting point for them to start saying, what do I need to do differently? Is it, once you have that baseline established, what's the first exercise program for them to start, losing weight or, shedding in terms of becoming more efficient?
Yeah, so if you're not worried about any design changes, you're not replacing chillers, you know where you are. Basically all these models can be applied to the same control sequences that they might already be tackled. So chiller staging, evaporator temperature control, primary versus secondary flow and staging, cooling tower optimization, maybe variable condenser flow. I mean, those are the big ones on the control side. And then the other piece is optimization. And, the control is, that's the fun stuff. That sounds the sleekest. It's a cool thing that everybody likes to work on, but a lot of times, honestly, on the fault side, those ECMs tend to be, they pop up, they're more of a mystery, nobody notices them. That can degrade plant efficiency a lot more. So my first step would be start comparing like equipment to each other, comparing it to performance data, your machines, those chillers. The health of your chiller is really important to maintaining and driving kW per ton lower. Reduce any risks that will cause plants to go down for extended periods of time, or understand where your peak capacity bottlenecks are. So you can tell the story of your efficiency, your dollars and energy. Can you then tell the next on where your bottlenecks are at the peak capacity? What limitations you might incur. Like, do you know how cold your condenser water can go on those chillers, right? So there's some questions and process you want to go through before you start bolting on sequences or really pushing that next level. And that's kind of what I have here, right? So
Yep.
you want to be, BACnet, we're big proponents of that. Pretty much all these softwares and anybody you're going to talk to, including ourselves, to optimize stuff that's going to go over BACnet. You got to make sure you have the right inputs on chillers. If you have a new plant or a plant that's 3 or 5 years old, and you have BACnet cards on your chillers, but your billing automation system only shows the operators like 6 points, or you're not collecting data on, your purge or your subcooling temperatures or your refrigerant saturated temperatures, right? That should really be a next starting point. So you get data beyond the BAS to start to catch the faults, to see how the chillers are going to change and be able to validate stuff that you do implement on the control side. And you catch when something's not a control issue. Oh, this is an expansion valve, or we just did maintenance in PM and brushed these tubes. How come our approach temperature is 4 degrees worse than before, right? Those are the things that really need to move forward first, and advancing chiller plant optimization. And then lastly, again, tag team with having data. If you're optimizing stuff, there is feature engineering that goes into this, right? If you're predicting thermal systems, you want to know, like, what's the 4-hour lagging wet bulb? How many degree days have I had this day? Versus, oh, it's 85 degrees and a dry bulb and a wet bulb of 65 right now, right? So there's things that build up and exist in, the tower efficiencies and what load they're running at, how much flows on the loop. So there's other feature engineering, kind of the technical term for, how optimization can be applied. So where is AI the easiest? I'm just wrapping up my last couple slides here, then we'll ask questions. Honestly, new plants and plants with identical chillers, if you're starting from, hey, we don't really have any sequences, we're in the design phase, or you have a newer plant that you're at, that we run a 85 fixed wet bulb, we've never looked at any of our staging sequences, and you have that big jump where you can show savings. Peer-to-peer comparisons across chillers and how they react is always a good one. Typically, new plants, new construction, though, you're going to get better attention and answers from your service providers, engineers. There's going to be a warranty period. Putting AI on a plant that has a mix of old machines, it runs in too many operating conditions. One chiller might have 300 data points that you can do data analysis on, and another has 5. Those can kind of be tricky scenarios where you end up with a little bit of engineer guesswork, or you might not be able to get all the way there, right? That's the world we live in, so you do the best with what you can, but I would encourage people to kind of ask questions, try and push the limits, especially on newer plants, chiller selection. So summarize, data is key. Validating machine learning is very important. Be aware of black box ROIs. A lot of software packages and offerings can be very disparate, even though they're all under the umbrella of chill water optimization. And monitoring and faults can degrade plant efficiency just as much or as more as your advanced sequences. So you got to pair those together, fault detection and optimization. Machine learning can be done at the edge or the cloud. So again, if somebody is saying, oh, we can only do cloud, or we only do edge, it's important to kind of ask some follow-up questions on, well, tell me about how this works. What algorithms? Why are there limitations? How do you have fallbacks and safeties in place when things break down? What if there's a stale data? What if my equipment goes offline? What control modes do I go into, right? So there is a bit of engineering to take place beyond it. So the future of chill water, in my mind, and where, I like to continue to push us as BuildingLogiX, is I do think, AI is going to play an important role, not just in optimization, fault detection. I think in years to come, being able to help train operators and query data like, hey, show me the maintenance logs on this machine. Have LLMs summarize like what's happening in the data so you don't have to go hunt for it. I think pairing that with more advanced visualization, um, you know, going beyond our basic Metasys, Decigo, Niagara graphics, where you just see green lights when the chillers are running. We got to take it to the next level to give people the tools. Not that they have to be data scientists, but have important metrics and better data visualization on building automation systems. Because this isn't an easy button, but there are practical options to move forward. And I hope that's one of your takeaway. And then again, you don't have probably vibration sensors on your pumps, chillers, motors. How do you detect shaving in oil? There's not a sensor necessarily for that. How do you know the health of your control, seals, your electronic control boards? Downtime will never go away, but there are building blocks. And this is a mock-up of one of the, say, preliminary things we've been working on behind the scenes. How do we have a lot of, I'll call it innovative visualizations from years ago on the chiller portal and BDX, and just being able to compare plants and machines to each other, looking at that over months and years at a time, being able to download that to use in machine learning. But we're continuing to think, how do we take this further? Like, you have a bunch of plants on a campus. Who's putting out the biggest tonnage right now? What efficiency range do they fall in? Where is flow going? How does your total campus efficiency across all plants? Like, do you need to, right? We haven't even talked about shifting load across different plants or pre-cooling loops for demand shedding. So, LLM summarizing data and rules that engineers have created and curtailed to sites paired with data visualization and advanced sequences is the future. And I think we're continuing to step closer to that. We're still in the early adopter phase, but the backbone of this really revolves on Python in my mind. So, there's this disconnect of machine learning and academia and tech to HVAC. Building automation systems can't do a lot of machine learning or are inhibitor and gateway between it. So you need third-party tools. So to scale, to get more prevalent, Python can be a good gateway to bridge that ground. And you don't realize, but you are influenced or deal with Python or C Python all the time. It runs behind the scenes in a lot of your computer products and a lot of your social media products. It's the backbone for a lot of what the big tech companies have built. And the beauty of it is that a lot of it is open source. So these are the example companies, their products and models that you can use in HVAC and chiller plant monitoring that they've just put open source in Python. So there is, a lot of movement in this field, and we're excited about it. I think it's going to, revolve around Python. I will say, we want to help promote this and, be a part of solutions. And I think Nick mentioned, all the states that we do monitor and have BDX on chiller plants with lots of data. We're considering rolling out kind of a little survey, and we did this in the state of Ohio across 400 school districts years ago, where they were like, hey, Energy Star is great, but how much are we actually spending? How are utility rates, EUIs compared to one another? I think we're going to put together a little questionnaire and survey for people to see, like, do you consent to share anonymous data, or do you want to submit where your plant runs? And anybody who kind of contributes can also see the aggregate results. How are plants running? Well, how is a variable flow efficiency in the real world versus primary, secondary, train versus Daikin machines? So if there's interest in that, please let us know in the comments or reach out to Alex and I. We're kind of formulating some early ideas and guidelines around that, but nobody's taken the lead on this thus far. And I think this is a question the owners are really interested in. So we can help facilitate some of that anonymously or, continue to educate. We're happy to do that. So with that, I hope this was helpful. If you have feedback on what I could have spent more time on, what you'd like to hear about in the future, what you might need help with, please reach out. Thank you again. Sorry we're a little over, but that happens sometimes. I hope it was worth it. Any questions? I think you can put them in the chat. Or there's
put
a
them in the chat or
Q&A.
the Q&A, either one.
Or if it's a question about your specific site or plant or something, you want to follow up with us after, that's fine too. Always just kind of happy to talk.
Yeah. Great job, Dan. So
Yeah. Thank you. Thanks for a couple of those who put in some questions. So,
Yeah.
all right. Well, I'll hang out for another minute or two. Kalevi, can neural net be implemented in Niagara? So it depends on how complicated your neural net is, right? So you look at a neural net will have a bunch of different inputs. And again, these are used for more complex problems. So it's not out of the realm of possibility that your neural net could have 50 to 100 inputs. I kind of like to engineer things a little simpler. So you might go through different iterations of, neural nets and forecasting and machine learning to kind of figure out what features are most relevant, what have the biggest influence. And
so he just added something to his
300 neurons
comment there.
Yeah, so neural nets, they require a lot of data, and I think you might have asked it last time. What's better, one layer, two hidden layers, etc.? Depends on the problem you're trying to solve. Starting point, I like to start with one layer to keep it a little simpler and see, like, all right, in the get-go, give the neural net plenty of time to compute. Let it run through its paces, give it a lot of options, and then do some statistical analysis on like what weights had the biggest impact. And then add in, did you feature engineer things in too? You're not just sending raw variables, you're sending lagging values, calculated values in. Then start to pare that down to the, either what from an engineering perspective or statistical perspective make the most sense. And if you can get it pretty small where the neural net is an output of a bunch of different coefficients, you probably could architect it in Niagara. It would be very, I'd say, time consuming. So my alternative to that is it'd be better to run a Python server that is doing the analysis, data crunching, CPU stuff, so you're not running that on a Niagara server, and then either through like the HTTP driver or like we've done it through, because of IT requirements, through like file sharing where you're effectively writing the set point to the Niagara server in the file space Niagara is allowed to access and picking up the set point there and then having safety logic in Niagara. That would be a way to deploy a neural net in conjunction with Niagara. But yeah, those are generally the more difficult ones to deploy. That's typically why I lean towards like decision trees, ensembles. But if you're getting into hybrid or reinforcement learning, you're going to have to run that on a separate server and then pass it to the building automation either directly through PackNet or through an API means into Niagara or something else. Let's see. All right. Well, yeah, I appreciate your guys' feedback. Sounds like this was helpful and informative. I tried to design it in a way that what's something that I haven't seen be done elsewhere, either at a conference on a webinar. So I hope some of this was new and maybe rightfully so, a little more technical for you. We'll hopefully see you at a conference or do some more chill water webinars like this if we get interest. But again, keep in mind if you want to compare plant data, participate in our peer study, we're formulating it all. Happy to talk. So any other questions?
I don't see any others.
All right. I see there's still a handful of people online. I don't know if they're eating lunch or just hanging out to listen. So thank you all. And yeah, we'll make the recording available if you want to rewatch it. We'll send out our
Or
YouTube
share it
link
with others. Yeah.
Yeah, likewise. So appreciate your time and yeah, stay cool.